Okay, that was the solution to this problem. Now I'm going to slightly change the question. Consider these numbers 1, 3, 3, 1. Let's say I have now 2 marked reds, 2 unmarked reds, 2 marked blues, 2 unmarked blues. Therefore, now my sample space consists of 2 unmarked and 2 marked blues. And with reds, I have the same configuration. Okay. Now, what is the probability that I pick a red? Again, 4/8, a blue, 4/8. These are still 4/8. What is the probability that I pick a red if I tell you it's unmarked? Probability red given unmarked. Red given unmarked is, this is the new sample space, so the probability is 2/4. Or what is the probability that I pick an unmarked given it's blue? So this is the new sample space, and unmarked is 2 divided by 4. So 1/2. Observe that this equals probability red without this information. And this one also equals the probability unmarked. So what do we see here? This information that the ball I pick is unmarked does not change the probability assignment you select for the red ball, the red outcome. Similarly, the information that the ball is blue does not change your probability assignment to the outcome of an unmarked ball. So this we call independence. Events A and B are independent if probability of A is equal to probability of A given B. So this means the occurrence of event B has no effect on A. Okay, so if I give you the information about event B occurring or not occurring, if you do not change your probability assignment to event A, then we say that A and B are independent. And independence is mutual. So if A is independent from B, B is also independent from A. So if you have this, this also implies probability B equals probability B given A. And obviously, if you plug this in the definition, probability of A equals probability of A given B, and probability of A given B is by definition equal to probability of A intersection B divided by probability of B. And then you put this to the other side, you obtain this probability of A intersection B equals probability of A times probability of B. So this is a little bit the product rule we talked about in counting techniques. If events A and B are independent, then the probability that they occur simultaneously is equal to the product of their probabilities. But this is not a general rule. Be careful. This is only when A and B are independent. For two events, this equality also implies independence. Now, see, we didn't define independence from this. This is a consequence of independence. But if you are considering only two events, this also implies independence. So if this is satisfied, you can safely say that events A and B are independent, which means, well, this is the definition. This will hold. But be careful. This is not true for more than two events, okay? Which means if you see that probability of A intersection B intersection C equals probability of A, probability of B, and times probability of C, if this is the case, you cannot say A, B, and C are independent, okay? It works the other way. If you know that A, B, and C are independent, this is the result. This is the consequence. But if this is true, it may be the case that they are not independent. Okay, it's not guaranteed.